Hey, nice to see you again. Welcome back to part 2 of Trig Identities. And what we're going to pose now is this question right here. Can we see it? Would the sine of two angles added be equal to the simple sum of the separate sines of those angles? What do you think? Could you actually find a relationship? Would it be like that? Let's have a look at this unit circle. If we've got A as that obtuse angle and B is this acute angle, then A plus B would be, well, B's about here, be around here somewhere, wouldn't it? Adding another B there to get a big angle, A plus B. Well, what do you reckon? Well, the sine of A plus B would be the x is the cos and the y is the sine. So that would be over in that quadrant there. What do you reckon? Would it be the simple sum? Don't know, because this could be as big as what? Root 3 on 2. And this could be, I'm just taking some examples here, a half. And if you added those up, those two separate sines, what would you get? Root 3 plus 1 on 2. And that's, well, root 3 is approximately 1.732, isn't it? Plus 1, approximately 2.732 divided by 2. Hey, that's greater than 1. So individual sines might add up to a value greater than 1. But any sine is the y-coordinate of the point travelling around that unit circle, and it's got to be less than 1, doesn't it? Got to be less than or equal to 1. See, here it is over here, A plus B. Its x and y have both got to be less than 1. They're still living in a unit circle, a one unit radius circle. So it doesn't look like this is going to happen for us. Like the sine of two angles added is not going to be equal to the addition of the two simple sines. Because if it was, you'd get situations where the sum was greater than 1, which is not possible for a sine of any angle, even if that angle is a sum. What is it then? What is the connection? How complicated is it? What is the connection between the sine of two angles added and their individual sines? Interesting question, isn't it? I want you to come down and have a go at seeing what you think about this. So here's a diagram for you. Okay, and I want you to think about, as a budding young mathematician, how you'd go about doing this. Well, there's our diagram. Maybe, here's a hint, maybe you wouldn't start with the sine. Why not? Think about the tools you've got. Why might we not start with the sine of A plus B? Okay. If we've got an angle. Well, there's more, I think, or it's easier to actually use in a case like this, maybe the cosine rule. Maybe we would look at the cosine rule because we've got some sides and just working with one angle. The sine rule needs two angles within the triangle. And we'd be searching out a relationship for a single angle, and maybe it would be better to use the cos, which relies upon sides and just one angle. And then if you look at what we've got over here, we've got a nice closed figure. It's a triangle, and we usually in maths want to use a closed figure because we've got rules that we can use within closed figure, particularly triangles. So this leads us to look at this, and maybe we start thinking, well, what about using the cosine rule in this closed figure? What angle could we look at? What is the angle? There it is in there. The angle in there in this closed figure is not A plus B, it's A take B. So for those reasons, just thinking it through, how you might doodle with a diagram like this to see if you can play with some relationships here, you might like to start off with the cos, because look, you've got the two sides here, okay, and the angle you might choose is the angle A take B, because it's naturally coming from this figure over here, it is contained in there. And then we might be able to build relationships for plus A plus B and sine A plus B later on. So that's a rationale. We'll go seeking now a way in which we can relate cos of the angle A take B to the individual causes. And we know now that it's unlikely to be cos of A take cos of B, because of what we were discussing about the constraints within the unit circle. So are you ready for the journey? Do you want to do a little bit of dabbling yourself with that triangle? See what you can do in here. 1, 1, A take B, and you could find that side, PQ, using the cosine rule. It might be a start. You want to play around and have a look at it a little bit. You can pause the presentation. I'm going to go on and look at the proof coming out of Hayes and Harris publication. So pause it, have a go, and then come down with me in a minute. Okay, coming down here now, here's the cosine rule used in that triangle. Here it is. This is the angle A take B. So let's do what I suggested you do. Work with PQ. Now, this is using a distance formula, and then we're going to do it using the cosine rule. Let's do the cosine rule first. Cosine rule says the square of any side is the sum of the squares of the other two minus twice the product cos of the angle opposite. So we've been able to actually get a formula which involves cos of A take B. Now there's another way of getting this length here, PQ. Look at it, distance between 2 points. The distance formula is the square root of x2 take x1 squared plus y2 take y1 squared. Remember that stuff. This is the idea of maths learning. One of my favourite things, the Huddyism here, is that maths learning is sequential and cumulative. You need to accumulate the skills in a certain sequence as the subject develops, as the branches develop. Okay, so here we are. Do you agree? Cos A take cos B, x2 take x1 squared, y2 take y1 squared. And when we expand it, just remember, first one squared, twice the product, perfect square expansion, plus second one squared, doing the same thing here, first one squared, twice the product, second one squared. Then if we collect up some of these cos squareds and sine squareds, well, that one collects those two, and then cos squared and sine squared here collects there, and then we've got this on the end. Okay, so this is 1 plus 1 minus 2 times that, or 2 minus 2 times that. Gee, look at these two. Aren't they similar? So in other words, PQ squared is this thing, or it's this thing. So guess what? We can say this term has to equal cos of A take B, because 2 times twice the cos of A take B is equal to 2 times twice this expression. So therefore we can deduce, I've rubbed myself out there, we can deduce that cos of A take B is cos A cos B plus sine A sine B. Comparing and equating 1 and 2, just put them equal and see that this is the result. Wow, that's complicated. Can we use that now? And I hope you enjoy the beauty of this. This is a beautiful derivation. showing you how to join together things that you know from quite junior burger maths there and get an interesting result as mathematics develops in your world. Okay, sequential and cumulative. Let's come down and have a look at how we can use this to reach other results. And here they all are here. So that's the one we just proved. Okay, and it was nice with the cosine rule. Now here, if you want to find the cos of A plus B, you could call A plus B A take neg B. And we have a rule for the cos of one angle minus another. It's the cos of the first one by the cos of the second, here it is here, neg B, plus, that's unusual, sine of the first by sine of the second. Are you seeing that? This is another favourite Huddyism here of mine, is this is a generic formula. You mustn't get based just in A's and B's. This is saying the cos of an angle minus another is the cos of the first, cos of the second, plus, this is unusual, cos of A take B is plus. Did you notice that in that derivation? Cos of A take B is cos of the first, cos of the second, plus sine of the first, sine of the second. So if we're taking away neg B, then cos A cos neg B plus sine A sine neg B. Do you get it? And the cos of neg B is the same as the cos of B. And the sine of neg B is minus the sine of B. This is the sequential and cumulative stuff I was talking about. We have to use those from our previous, here they are, our previous trig identities back in part 1. Okay, see how it builds. You must build up these skills and abilities. Okay, and then if we simplify that, it's cos cos, and that positive by that negative is a negative sine sine. So there's an interesting result here. In cosland, if you're finding the cos of a difference, it becomes the sum of this these couple of products. And if you're looking at the cos of the sum of the angles, it's actually down here, the products with a minus, it's subtraction of those. Why is that so? Well, that's come about from applying the cosine rule, hasn't it, in that derivation before. You might go back and track that. Well, how would you do sine of A take B? Well, I know. There's an intimate connection between sines and coses, isn't it? Do you remember? It's written down here. If you want to connect the cos of any angle to the sine, then the sine of 90 minus that angle equals the cos. And the cos of 90 minus that angle equals the sine. These are previous trig identities. I hope you've accumulated that knowledge from the first presentation. So let's do it over here. The sine of A take B is the same as the cos of 90 take A take B. And then we can say, well, okay, we could regroup this. It's the cos of 90 take A plus B. So that's the cos of the first, cos of the second, cos that's a plus, it's a minus in there, sine of the first, sine of the second. We're using this one to build. Hey, that's a pretty common theme in the derivation, the build-up of various branches of mathematics. Once you've established with deductive reasoning the validity of something, you can go on and use it and build. So we've now switched to sines. So the sine of A take B, let's have a look at it. Cos of 90 take A is the sine of A. All right, remember that. That's this result over here. The cos of the complementary angle is the same as the sine of the angle. Cos B, let's leave it. And then minus, okay, sine of 90 minus A is the cos of A, the sine of B. All right, do you notice if it's a difference between sines, that stays the same there? Well, this is going to be hard to remember this pattern. And how are you going to remember this? Well, the sine of A take B, sine of the first, cos of the second, minus cos of the first, sine of the second. That's generic land. Don't get hooked on just A's and B's. A and B, as you will see in these derivations, could be anything. We're putting negs in there as well. So what about the sine of A plus B, where I first started? We know from our reasoning before, it's not going to be just sine A plus sine B. You bust the unit circle. You go past 1. But you could call it the sine of A take neg B. Okay, so that's sine A, cos of neg B, and then from using this up here, minus cos A, sine of neg B. The cos of neg B is the same as cos of B. The sine of neg B is minus the sine of B, previous identities. And so then you get the sine of an angle sum, sine of the first, cos of the second, plus cos of the first, sine of the second. So I think the sine ones are a bit friendlier. Why? Well, if it's a plus in there, it's a plus between the two products. If it's a minus in there, it stays consistent. Whereas in cosland, this is a plus up here, but it's a minus in there. Wow! Have you got a headache? I guess you have. But all we've got to do now is try and remember those patterns or write them down. So let's come down, and here they are written down for us. Just please remember, I want you to have a generic approach to this. Don't just think it works for A's and B's. Cos of an angle plus another is cos of the first by cos of the second. Cos is difficult because it changes the sign, and then sine of the first, sine of the second. So I remember this as a cos, sine, sine. So coses, when you're adding or taking angles, it's cos, sine, sine. And you see the idea? I'm just writing cos, and sine, sine. And the way I remember it, it's the opposite sign in here. The pluses and minus are opposite to what is in the original sum or difference. So let's see if I can make that clear. Cos of A take B. I look at that and I say that's cos, sine, sine. But it's the opposite to that. So it's cos plus sine, sine. Okay, I'm trying to help you remember these so you don't have to look them up all the time. You want to be a really, astute and gifted mathematician, don't you? All right. So what about the sine, these two? Sine of two angles added, two angles subtracted. What's the pattern? Sine cos, cos sine. And it's got the same sign in here. So if it's sine A plus B, I put sine cos, cos sine, A and plus. If it's a minus in here, it's an easy one to remember, it stays in the pattern. So have you got any idea now? Cos of two angles added or subtracted? What's the rule? Cos, sine, sine. Reverse the pluses or minus between them. Sine of two angles added or subtracted. What's the pattern? Sine cos, cos sine. With the same plus or minus in between them. All right? These are called addition formulae. Addition formulas or formulae, if you go back to the Latin plural of that word, formula. Okay, addition formulae. Enabling you to find the sine or the cosine of two angles added. And we'll do the tangent one a bit later on. Okay, are you ready? Let's do some stuff with it. And again, simplification is made a lot easier with this now. Okay, so let's expand this. Sine of two angles added, theta and phi. So it's sine cos, cos sine. Got it? And if it's minus there, it's minus here. So it's sine of the first, cos of the second, minus cos of the first, sine of the second. Got it? Okay, let's look at this one. It's a cos. So cos, sine, sine. Cos, sine, sine. Got it? And the plus becomes a minus here. Cos of the first, cos of the second, minus sine of the first, sine of the second. It gets easier if you do your lap running, if you do the practice like an athlete. You're a mathlete, aren't you? You've got to do those maths exercises to keep up with it all there. Okay, so I want you to have a go from Hayes Publications now, 4F3, question 1, and I'm going to show you down below the answers in a minute. Okay, so pause it, have a go. Here we go, here are the answers now. So check those out. Are you getting the pattern? Sine, cos, cosine. Okay. Now, see this? I don't like the way they've done this. I prefer you did sine m cos n and then cos m sine n. All right, because of that sine cos, cosine. Keeping them in that order. This is correct, but it doesn't actually help you remember the pattern very well. All right, let's go on. What else can we do? This is getting exciting, trying to break down these relationships now. So what about this one? Sine of 270 plus alpha. And check your answer with alpha being 20. All right, we got a sine. What's the pattern? Sine cos, cos sine, a plus and a plus. So you've got it in one. Put in sine of 270, which is neg 1, 3 pi on 2. Cos alpha. And the cos of 270 is the x-coordinate. It's right on the axis there, remember? 3 pi on 2 is 0. So it's minus cos of alpha. And you could actually put it all on the calculator. 270 plus 20 is 290. And does it come to minus the cos? Yep, check it on the calculator. All right, have a go at these now. Pause the presentation. I'm going to show you the answers in a minute. Okay, coming down to the answers, there they are. How did you go? Hope you're getting some skills here. If you're not sure, go back and have a look. Maybe write out those formulae again. Let's keep going. I've got more for you yet. There's an exciting presentation, this one. Really empowering you to work with lots of different trig identities and trig expressions. All right, cos of theta take pi on 6. Then simplify your answer and put it like that. Let's look at the first thing though. All right, it's a cos of two angles subtracted. First of all, cos in our in our addition formula, and subtraction formula if you like, although you don't call it that, it's the addition of a negative, it's a subtraction, is the pattern cos cos, sine sine. Just remember, cos has a reversal there. Okay, so you'd want picking one of two patterns, sine cos, cos sine in sine land. And cos is cos cos and sine sine. And in that cos one, you've got to reverse the plus or minus in the middle. So let's evaluate cos of 5 pi on 6. Working angle of pi on 6, so the cos is root 3 on 2. It's in the second quadrant, so it's negative. Remember all that old stuff. Sequential and cumulative must build up your, in sequence, your knowledge here. Sine of 5 pi on 6. Working angle, pi on 6. Sine of pi on 6 is a half. Second quadrant, still positive a half. So you now have it in the form required. And you can look at this going back to the unit circle to determine those things as we did in earlier work. Okay, now we have got it in the form A sine theta and B would be neg root 3 on 2 because they've said plus B. So we've got a B here of neg root 3 on 2 cos theta. Okay. Pause the presentation, have a go. I do each of these just so you can build your skills up. Must do your lap running, you mathlete. Okay, I'll show you the answers now. There's some answers for you. Okay, check it out. Powerful stuff. Getting up close and personal with some complicated looking expressions here. Okay, let's keep going. What more can we do? Well, there's a few little things yet. Now, let's have a look now. Wow. What's this? Okay, it looks complicated, but I think you might recognise the pattern. Do you see it? Cos, cos, and sine, sine. Well, we're going to go in reverse now. We're going to package it back up into a sum function. Now, this is an addition formula, and we're going to go backwards. So we recognise this, so we say that's a cos, and if it's a minus in here, we know we reverse it in there. So that doofy is really, with the reversal of the addition formula, is cos of 4 theta. Hey, that was neat. Okay, could be a lot of value in packaging them back up into a cos or a sine of two angles added. All right, so what I want you to do is to work backwards through each of these. Remember, you're trying to spot two patterns. Is it cos, cos, sine, sine, or is it sine, cos, and then cos, sine? This one has a matching plus or minus. there as matching with the sum function, and this has the opposite sign. Little tricks there to help you remember the formula without having to look them up. Okay, I want you to pause the presentation, have a go at all of these. It won't take you long if you're on the ball there. And I'll show you the answers now. Come down here. Oh, there they are. Lots of answers there. Great. Make sure you've had a go and go back and try again. Talk to your classmates, talk to your teacher if you're not sure. Right, let's move on. Not far to go now. There's a lot happening, isn't there? Okay, without using your calculator, show that sine of 75 is this doofy. Okay, so we want it in an exact third form, so the calculator won't give that to you. Well, it may do. You can wiggle it around to do that, but let's do it without a calculator. So what's it got to do with this? 75 is the sum of two common angles, and we know they're sines and coses, so we won't need a calculator. So the idea is to take the angle and break it down into common working angles. Sine of a sum, that is sine cos, cos sine. And if it's plus, it matches. Remember that? Hope you're getting good. Sine of 45 is, I don't like 1 on root 2 because that's not the simplest third form. You multiply 1 on root 2 by root 2 on 2, you get root 2 over 2. Right, root 2 by root 2 is 2. And that's deemed to be the simplest third form because it's got a whole number in the denominator. Okay, so I prefer you put that in there, but it doesn't matter. You'll come to the same thing at the end. So you put in all these common values you're supposed to know. And if you do that, and then you end up multiplying by root 2 on root 2, I think it's better to do it up here. They should be root 2's on 2 already. And you get the required answer. So there's a little tricky do. You know, some of these angles here, you can actually break down to common angles and get the exact third form proudly, notice that, proudly as a mathematician, without the calculator. Because I want you to be proud that you can do it with mathematics. Okay, pause the presentation, have a go. I'm going to show you the answers. Oh, well, you got the answers there, sorry. Okay, so there aren't any answers for this one because it shows you what to do. So you must start just with the left-hand side and make sure you clearly show the result. And then at the end, as we mentioned in an earlier presentation, put as required. Any proof here should be finished with a sign-off that you have achieved what was required. All right, let's go on and have a look at what more I've got for you here. So here's another challenge. So we've got sine of this plus cos of this one. Okay, so we can break them all separately. Sine is a pattern. Sine cos, cos sine, with a matching positive in there. Cos is cos cos, sine sine. And the sign in the middle is opposite. And then we could just put the numbers in. Sine upon 6 is a half, leave cos alpha is cos alpha. Cos upon 6 is root 3 on 2, leave sine alpha. Cos upon 3 is a half, leave cos alpha. And then sine of pi on 3, root 3 on 2. So if you look at this, hey, that goes out with that. And you've got a half cos alpha, another half cos alpha. You've got 1 cos alpha. How about that? And they're putting this around here as one way of trying to remember the sines and coses of those common working angles. Okay, so these will show that, so be careful with show that. You must give reasons for your mathematical argument. Otherwise people will accuse you of spotting it and fudging it. Okay, so be careful with your mathematical explanations. All right, have a go, and particularly have a go at D. You might have to check that one by talking to your classmates or teacher. Pause it, have a go, and I'll go on. Okay, we're coming to the end now. And I want to do what we have been doing with sine and cos. This is less popular because tangent is not as prevalent in our world as we know it as sine and cos. You might think, why is that so? Well, I suppose one simple reason for it, if you're just looking at applying mathematics in a simple way, is that periodic functions are more prevalent. We've got periodic phenomena, as we've discussed in earlier presentations, and sine and cos actually model those very well. There are less situations where we want to actually deal in practice with tan functions. However, let's look at them now. The tan of a negative angle is minus the tan of the angle. You might like to try proofs for these, like we did in the last presentation for similar identities with sine and cos. Tan of the complementary angle is 1 on the tan of the angle. That could be interesting to prove. Might have to prove with tan these results by going back to sine over cos. Just remember that y equals tan x, that function, is equal to sine x over cos x. So there is a way of proving tan relationships by reverting back to the sine over cos definition. And we're going to prove one of these, but not all of them. Tan of A plus B, tan of the first plus tan of the second, 1 minus the product. Okay, just watch that. That stays the same. And when it comes to minus, this is minus. So it's the tan of the first minus tan of the second, and this is the reverse sign. They reverse in the bottom line. That's the way I try to remember them without having to look them up all the time. I don't think students want to watch me doing maths and teaching them if I have to look stuff up all the time, and you want to be the same way. And then tan 2a, I wonder how you could prove that that was 2 tan a over 1 take tan squared a. We haven't done that with sine and cos. That's the last presentation 3. But you might like to look at this right now. Do you want to play with this? Tan of 2a. You could call it tan a plus a. Do you want to pause the presentation and have a go? Do that and see if you can come up with this result. Let's do it. Tan of A plus A. Let's go back to this. Tan of 2 angles added, tan of the first plus tan of the second over 1 take tan of the first, tan of the second. And the first and the second are the same. So 1 tan A plus another tan A is 2 tan A. Oops, I put B here. I said it was the same. Then I went and wrote B. I've got to get rid of that. So tan A. So this is 1 take tan squared A. As required. Okay. All right, got that? We've just proven that one. Are you excited about how this is developing for you? You can see you're not far away from doing some very useful deductive proofs yourself. Okay, let's come down and use those in a similar way to what we've been doing. Okay. Oops, too far there. I just juggled this around. So now let's do a proof for the first one. Tan of A plus B. That's the sine of the angle divided by the cos. Now let's do our new addition formula. Sine cos, cos sine, with the identical plus or minus between them. And the cos pattern is cos cos minus sine sine. And the opposite sign between them. Now here's a little tricky do that we quite often use in trying to simplify expressions like this. We divide every term by cos A, cos B. Now you wouldn't know this. This is a little algebraic trick that we could sometimes use. But if we divide every term by that, so we're doing it here and here and here and here. But now look what happens. We can say here, in this one, the cos B cancels. Sine A over cos B, sine A over cos A is tan A. Plus, and now these two disappear. Sine B over cos B is tan B. And down here, cos A cancels, cos B over cos B also cancels, that's 1. Then over here, sine A, sine B, sine A over cos A is tan A, sine B over cos B is tan B. This is often called a hybrid term, consisting of a combination of the sine and cos of the two angles. And when you divide through by it, because it's got a bit of both terms in it, you can cancel quite often. So there's that one proven, and in brackets, what would we do? As required. Okay, can you get the hang of this evolution of the trig identities here? Let's come down now and have a go at 4G4, and I'll show you the answers in a minute. All right, so have a go and see what you think. We've already done part D, which I asked you to do earlier. So pause it, and I'll show you the answers. So coming down now, there are answers to question 1 and 2. Okay, let's go down and do a little bit more, and then we'll finish. You'll be getting tired now. You're doing well though. So here's the example 45. Given values of tan A and tan B, can you find the tan of A plus B? So you write down the identity, tan of A plus B, tan plus tan. This sign remains the same as that. One take, opposite sign here, the product of the two. And then you're putting in the numbers. Tan A, tan B, one take, tan A, tan B. Working it out now, 13 over 3 divided by neg a third. You can think of it as equivalent to neg a third lots of 13 over 3. So some people get confused as to what to do with those two threes. So it's neg 13 over 9 or neg 1 4/9. Division by 3 can be thought of as multiplication by a third. That might help you, help some people. All right, so it's using those formulas now, expanding them and substituting them in without a calculator. So I'm going to bring a few down so that you can have a look now. Bit of work here for you. Question 3 through 8. I'm going to show you the answers in a minute. All right, pause the presentation and have a go. Try and do most of them. Let's go down and look at the rest now. 9 through 13. Okay. All right, now with some of these, just keep in mind, B is acute, beta is acute, means it's in the first quadrant. So you might discard the negative solution there, because all sine, cosines and tans are positive in the first quadrant. You might have to keep your wits about you as you come down here. All right, pause the presentation, finish those off. I'm going to show you the answers now. So coming down, here's some answers. The last few questions haven't got answers. They show that, so they tell you the answer. Be careful with those. Okay, one little thing to do, number 14. Let's have a look, and it's using what's called the duplication or double angle formula, because you're duplicating the angle. It's 2A. Duplication or double angle. We're going to be doing this with sine and cosine in the next and final presentation 3. Okay, so we want to find the possible values of tan alpha if we know the tan of twice the angle. Tan 2 alpha is 4 over 3. So let's write down the formula. Tan 2 alpha is 2 tan alpha over 1 take tan squared. Putting in the number on this side, and for convenience sake, letting t stand for tan alpha, because it gets very wordy, tans everywhere, if you stick with that. What can we do? We can multiply both sides by the common denominator, which is 3 outside of 1 take t squared. Okay, now they haven't shown that. That would give now 4 take 4t squared equals 6t. Okay, so multiplying both sides by that. And then if you put all the terms across the right-hand side, they haven't shown a lot of this. 4t squared plus 6t take 4, and then dividing both sides by 2. 2t squared plus 3t take 2. And that's what they've done. So there's a fair bit of work in between there, multiplying by that common denominator. That's the preferred mathematics. You can sort of remember it as that times that and that times that. That's not good mathematics. It's better to think of multiplying by the common denominator and cancelling out those denominators. Okay, so when you've got this expression equal to naught, you're probably going to invoke the null factor law. If you can change this to a product is 0 when one of the terms is 0 or null. the null factor law. So either this is 0 or this is 0. So t is a half or neg 2, putting those equal to 0. So I've left out a few steps there. But what I'd like you to do is to try and do that now, working backwards. Given tan of the double angle, or the duplicate angle, 2 alpha, can you find out what the tan of alpha would have been? Pause it, have a go at those two. I'm going to show you the answers now. So there are our answers for those two questions. Wow, have you got a headache? We're moving on at quite a rate now. And the idea is not just to get a headache, but to feel empowered, that you're actually getting somewhere and you feel confident with working with these expressions. All right, one to go in this series of presentations on trig identities. It's part 3, and I'll catch you then. It's cheers for now.